Good morning. I'm going to go ahead and do the making predictions probability lesson with you guys. That way, next week, you're not rushing to do 3 lessons in 2 days. This is the second probability lesson, which is supposed to be completed this week. Next week, you have 3 lessons: area of triangles, area of circles, and circumference. And all lessons are due by Tuesday, which is 6:30. So I'm also going to begin reassigning those lessons that some of you were not successful on. You only have to redo them if you didn't pass them the first 2 times. So you get 1 third and final opportunity. Our vocabulary is very similar to the first probability video. Probability is the likelihood that something's going to happen. Experimental probability is pretty self-explanatory. It's the probability of an event determined by carrying out a simulation or experiment. Theoretical probability is the expected probability of an event. And then sample population is all of your possible outcomes. And a proportion is a statement of equality between 2 ratios. Proportions are basically how you're going to make predictions using probability. For example, if you roll a 6-sided number cube, the probability of rolling a 3 is 1 out of 6. If I roll that same number cube 30 total times, how many 3s can I expect to roll? Okay, so this is how many times you did roll a 3, and this is how many total outcomes there could be. So if I roll it 30 times, how many times can I expect to get a 3 out of 30 total rolls? So what did we do to 6 to get to 30? We multiplied it by 5. So what I do to one side, I must do to the other. So 1 times 5 gives me 5. So you can expect to roll a 3 5 times. Now, is this always going to be perfect? Like if I grabbed a dice right now and rolled it 30 times, am I going to get exactly 5 3s? Maybe not. Probability is just an estimate. It's not always going to be perfect. That's why they call them predictions. All right, so if about 10% of the population is left-handed, use that statistic to answer the questions below. In a classroom with 20 total people, how many do you expect to be left-handed? Okay, so we're going to put lefties on top and total people on bottom. Okay, and we're creating equivalent ratios, also known as proportions. If I have 20 total people, that's going to go on the bottom. I don't know how many of those are lefties. I also know 10% of the population. So if 10%, in 6th grade, y'all should have worked a lot with percents and talked about what they meant. And hopefully you remember that percent is per 100, meaning that 10 out of every 100 people are lefties. So what did we do to 20 to get to 100? Or 100 to get to 20, my bad. We would divide it by what? 5. Can we divide 10 by 5? Yes, and that equals 2. So in that class, you would have 2 lefties. Okay. The next question says in a school with 1,000 people. So we're going to keep that proportion almost the same, but we are going to put 1,000 total people instead of 20. Now, what do you do to 100 to make it 1,000? You multiply by 10. So can we multiply 10 by 10? Sure we can. 10 times 10 equals 100. So you would expect 100 left-handed people in that school. And one final example, or not example, question. Are these numbers exactly how many people will be left-handed? So if we have 20 students in our bridge class, are 2 of them going to be lefties, or is this just a prediction? Well, with all of probability, it's just a prediction because in the real world, anything can happen. So we could have 10 lefties and then we're just not the norm. So all probability is predictions. If you have a batting average of 25 hundredths, this means the probability of you getting a hit is 25%. There's our percent per 100. So our hits is 25 per 100. Percent per 100. If you have 520 total attempts this season, how many hits can you expect to get? So if you get 25 out of 100 at bats, then how many would you get out of 520? Okay, this one doesn't come as naturally to me. I don't see the relationship as clearly. So I can also make myself a table and I can say I get 25 for every 100. I can also say that I get 50 for 200. I can say I get 100 for every 400. I can say 500 would be 125. And then what would 600 be? 600 total would give me 150. So I know that it needs to be in between here. Okay. Now, could I also work backwards? Could I say that 5 hits are how many at bats? 20. Oh, look, 520. Can I add 125 and 5? Sure, I can. So that is 130 total hits. So proportions can be your friend because you can work them almost any way. If you're really good with your multiplication facts, a lot of times you can see what you're multiplying by. If you're not so great at your multiplication facts, that's okay. Make yourself a table and just jump around in the table until it makes sense. You can also use a percent bar. Some of us are really good with percent bars and just jumping around with the percents that you're really familiar with. Really anything can happen with the proportions. So that's why they're a really easy way to solve these. Last example comes straight from Imagine Math, which most of these have. Juan is watching cars go by the road. He counts 10 out of 100 cars that are silver. This means his experimental probability of seeing a silver car is 1/10 or 10%. Statistics for the distribution of car colors in North America is shown. Okay, so this is here's experimental probability. This is theoretical based on the cars that have been sold in North America. So one's experimental and one is theoretical. Which statement is true? The information given in the table must be wrong because it does not match the experimental. Did we say that they were always going to be 100%? Remember the lefties question? You don't always have 2 lefties in a class. Sometimes you have 3. Sometimes you have 0. So I'm going to count this one as false because theoretical and experimental don't always come out to match. If he observed more cars over time, his experimental probability would get closer to the percentage given in the table. That's a possibility. We're going to keep that one for now. He must have miscounted because it does not match the information given in the table. Well, to me, this one relates back up to that first one. They're not always going to match. So sometimes Sometimes it's just not going to work out that way, the way your experiment happens. Think of time of day, how long did he watch, all that kind of thing. If he observed more cars over time, his experimental probability would get further away from the percentage. Do you think that if he was 5 off of the percentage, do you think the more he watches the cars, the farther he's going to get or the closer he's going to get? Because those are the two that we have left. I personally think the closer he's going to get, because the more cars, the more chance of them being silver. So I'm going to go with that one as true. And this one is false. All right, you guys. Good luck on these lessons. I am here for office hours every day from 11 to 12. I will be here, what is today? Tuesday, Wednesday, Thursday of this week, and then Monday, Tuesday of next week. So please check in if you need any help at all.